Hello and welcome to this channel. In this video, I will discuss large language models or LLMs. LLMs can write poetry, debug code, and pass the bar exam. But does a LLM know what it's doing? This is the core question facing every researcher in the field of AI. We are diving deep into the black box of the large language models architecture to explore if it's merely a sophisticated pattern matching machine or if something more profound is happening inside. A large language model is a type of machine learning program designed to understand, generate, and interact with human language. Think of it as a massive, advanced digital brain trained specifically on text. The fundamental function of an LLM is surprisingly simple, predicting the next word in a sequence. Large language models are true general-purpose technologies driving applications that span and impact virtually every sector of the economy. LLMs, like any other machine learning algorithms, try to find a statistical pattern in a massive dataset of content. A paper entitled "Attention is All You Need" was published in 2017, which introduced the transformer architecture. This architecture provides several advantages. It supports efficient scaling for multi-core GPUs. It enables parallel data processing for faster training on massive datasets. And most importantly, it utilizes an attention mechanism to learn the true contextual meaning of the input text. The transformer architecture uses self-attention to look at the entire input sequence at once. This allows it to understand long-range context and process data much faster through parallel computing. Here is the transformer architecture from the original paper. It consists of two primary components: an encoder that is responsible for processing the input text, and a decoder that generates the output text. Each component has two main sublayers: a multi-hit self-attention mechanism that allows the model to attend to different parts of the input sequence, and a feed-forward neural network that applies a point-wise fully connected layer to each position. Let's dive into the transformer architecture to understand the complete flow from how raw text is taken in by the encoder, processed internally, and how the output sequence is generated. For simplicity, we use a simple sentence: "Attention is all you need," the title of the original paper. The input is first tokenized and converted into numerical IDs called tokens or subwords. Note that there are three extra tokens: PAD, SOS, and EOS, that are control tokens or reserved tokens, and PAD is padding used to make all sequences in the batch the same length. SOS is the start of sequence, and EOS is end of sequence. These tokens are mapped to vector embedding. The embedding layer converts each token into a dense, high-dimensional vector. These vectors are trainable, and the intuition is that these vectors learn to encode the meaning and context of individual tokens in the input sequence. For instance, attention in the above sentence has following embedding. Note that the dimension of embedding varies, but in this case, it is 512. Also, positional encodings are added to preserve word order. For a given position in the sequence and a given dimension within the embedding vector, the positional encoding value is calculated using sine and cosine functions. Here is the positional encoding for the above sentence. Then, the input and positional encoding vectors are combined and fed into encoder stack through multiple layers of self-attention. The multi-headed self-attention mechanism calculates how every word in the input sequence relates to every other word. The output is processed through a fully connected forward neural network, producing a deep contextual representation of the structure and meaning of the input. Here is the output for that sentence. The final representation is then passed to the decoder. The decoder generates the output sequence one token at a time in an autoregressive loop. The decoder starts by receiving a startup sequence token. It uses the encoder's deep representation. The result will be fed into the self-attention and feed-forward neural network. After normalizing, a final softmax layer is applied, and the first token will be generated. This newly generated token is then fed back into the decoder's input, acting as a trigger for the next prediction. This loop continues until the model predicts an end-of-sequence token, completing the generated output, which is then detokenized back into human-readable words. Now, let's dive more into each of these components. The attention mechanism helps capture relationship between elements in a sequence by assigning different important weights to each element. It allows the model to focus on the most relevant parts of the input, improving its ability to understand context and handle long-term dependencies. The attention mechanism is composed of several components that work together. They are self-attention, that enables the model to weigh the importance of word pair relative to one another and understand the relationship between them. A scale dot product attention that computes attention scores between words in a sequence through dot product, scaling, and softmax. And multi-head attention that employs multiple heads to simultaneously capture different aspects of input data, such as syntactic and semantic relationships. Feed-forward neural networks are used to learn complex nonlinear relationship between the input embeddings and its context. And masked multi-head attention in the decoder prevents the decoder from cheating by looking ahead at future tokens it has not yet generated. To improve the stability and training speed of the transformer model, layer normalization is applied after both attention mechanisms and feed-forward networks. It helps mitigate the risk of vanishing or exploding gradient. So let's quickly recap what we have learned. An LLM is an advanced text prediction machine trained on trillions of words to understand human language context. It works using transformer architecture that relies on self-attention to weigh every word's importance. And remember, the future is arriving, so we must be responsible in how we use these powerful, bias-prone technologies. The best way to understand LLM is to start using them. Comment below what is the most mind-blowing thing you have seen in LLM do this week. Like this video if you learned something new. And subscribe to the channel for more deep dives into the tools and trends that are reshaping our world.
I hope this session clarified how LLMs work. Check out the next video linked here, and if you found this helpful, give us a thumbs up and subscribe.